Now, dear student, chapter number 4, motion in a plane, and we have the topic that position vector, displacement vector in term of rectangular components. So, already we have done this one topic in the part of the graphical notation, but here we are just assuming that along the x and the y axis, those are mutually perpendicular to each other. So, what are the position? How can we represent the position vector in term of the coordinates? Okay, so here just I am assuming the the point P which having its own coordinates, that is called the x and y we have. Okay, now I am just making the perpendicular to that x-axis, and here just I am representing the concern of the vector we have. uh, this one is a vector that is called the O2. Suppose this one is a nomination we have, that is called the A, and here we have the meaning of the perpendicular, and that is called the portion, and it was also represented by the area. This point is nominated as a B. Now this one is a vector that is called the xi cap, and this one is a vector that is called the yj cap. So these nominations we can assume here, and we will apply the simply the triangle third law. Okay, so I'm just starting the triangle third law, that to OP vector, and we are starting the moment from O to A, and then A to P. Okay, so simply we can write that the OP vector, that is called the R vector, x I cap plus y of j cap. This is the simplest representation we have. Okay, and in the part of the magnitude, easily we know that we will make the square of the components of the I and j. So here I am just easily writing that x square plus y square, or either you can go directly to apply the Pythagoras theorem. This one is equation number 1, equation number 2, equation number 3, or you can do the simply method that from triangle OPA, that means hypotenuse square, that is called the OP square, and that is called the OA square plus PA square. Okay, so this one is the simplest meaning we have. When OP is nothing but it is simply the meaning of the R we have. R square is equal to OA in the part of the magnitude, that is called the x square plus y square. So this is the another method we have, through which we have already we can get the simplest meaning of the magnitude. Okay, so this is the simplest representation of a position vector in the term of the rectangular component. Now displacement vector in the part of the rectangular components. Okay, so here I am just assuming the simply the motion of a particle in the two dimension, and I have assumed that the particle is moving along the curved path. So initially its a position vector can be denoted by the its a position vector can be denoted, and the particle is at the point P. It's having its position vector. Suppose this one is a r vector. Okay, now it's reaching at the another instant of time, that means point P dash. Okay, so it having its position vector from the origin O. From the origin O we have the position vector, that is called the P dash. Okay, here we have the OP dash, and the position vector can be represented by the, that mean R dash vector. Okay, so particle is moving from P to P dash, so there is a meaning of the displacement of a particle from P to P dash. So I am just representing it further by the simplest meaning. Okay, so P to P dash is a part of the displacement we have, and we are representing it. Mm, okay, so and along the direction of the displacement we have the direction of velocity. Direction of velocity we have. Okay, this one is the simplest meaning we have. Okay, now how can we make the assessment further? We are just approaching the triangle law of vector addition in the triangle, that means OPP dash. Okay, so how can we go through this? Two more nomination which I have assumed here, that point P having its coordinate, that is called the these are called the x and y, and the another that at the point p dash the coordinates are x dash and y dash. So here I can how can I use the simplest method of the triangle of vector addition? Apply triangle law of vector addition in triangle OP P dash. So we know that two sides should be in same order and the third side will be in the opposite order. So I am just writing OP dash OP dash, that mean vector, that is called the OP vector plus PP dash vector. Okay, OP dash vector is a simply, and we have to be find out the meaning of the displacement, so we are just separating it. PP dash vector is equal to OP dash vector minus of OP vector. So what actually I am getting, uh, this is called the, this portion is called the delta R, that is called the displacement. So here just I am representing delta R is equal to R dash vector minus R vector. So this is the simplest that means portion, but we know that as the particle is moving from P to P dash, so in the part of the coordinate system, the R dash which we are using here, that is called the x dash I cap plus y dash j cap, and R can be utilized here, that is called the x I cap plus y and j cap. Okay, so if I am just drawing the perpendiculars on the x axis, so these are having its own nominations. This one is called the delta x we have. Okay, this one is called the delta y we have. Now we are just using all the things. This is equation number 1, equation number 2 and equation number 3. Use equation 3 in equation number 2. So these are the general methods we have to represent the rectangular components of a particular vectors. Okay, so delta r can be stated in the part of that r dash, x dash I cap plus y dash j cap, minus sign is there, x I cap plus y of j cap. Now we are just making the common of the I cap is there, so x dash minus x I cap plus y dash minus y of j cap. So further we are just simplifying it, so delta r can be stated in the term of that delta x I cap plus delta y j cap. Here just I am not representing because it's a part of the magnitude we have. So this is the basic concept to resolve the, that mean rectangular component of a displacement vector. So the particle having its own displacement along the x-axis as well as on the y-axis in the two dimension. So this one is a generally case which we are discussing here in the two dimension. Okay. Now more things we have. Now the some same topic which is attached to this graphical portion or rectangular components. Now expression of the average velocity in the term of the rectangular component. So how can we find out, and we will take the help about of the rectangular component from the graph. Okay, the average velocity of an object is the ratio of the displacement to the corresponding time interval. So we will take the help of this graph of the, that mean rectangular component of displacement vector. So from this graphical section we can easily go through it. Okay, so the average velocity is a simply representation that I am just putting the nomination of the average on the v. Okay, now this is the kind of the displacement of a particle, and this divided by the delta t. Now we know the delta r can be stated in the part of the delta x of I cap plus delta y of j cap, and corresponding time intervals, that is called the delta t. Okay, further we are splitting this one term, delta x I cap upon delta t plus delta y upon delta t and j cap. So in the part of the rectangular component, this one is the average velocity along the x-axis. This is the average velocity along the y-axis. So we have the simply notification that is called the velocity along the x-axis, that is vx I cap plus vy average j cap, and these are in the part of the magnitude. So this is not a vector, this is a part of the average we have. Okay, so here we can show the average velocity is equal to vx I cap plus vy j cap, है ना. And direction of average velocity is same as that of displacement vector. So this is the general representation we have. Now we will talk about the instantaneous velocity. This is the further part that is coming on behalf of the differentiation. So what is the meaning of the instantaneous velocity? Limiting value of its average velocity when delta t approaches to 0. So this is the basic concept we have, and already we have done, but further we will do it here. So how I am just representing the formula of the instantaneous velocity. So instantaneous velocity, in another word, although can be stated as the velocity of an object at the particular instant of time. Okay. So generally we have discussed that the limiting value of the average velocity. So I am just applying the limit delta t tends to 0, and here we have the displacement upon constant time. Okay, so the derivative portion, it is a derivative portion, so d bar by dt of the displacement we have, that is called the dr. Okay, so this is the concern of the average instantaneous velocity. What actually it is? Instantaneous velocity. Now on behalf of the graphical notation, we can approach the direction of the instantaneous velocity also. So these graph are given on the page number 73, page number 73 NCERT book. Okay, so I am just pasting all the graphs here regarding to the that mean how the average velocity convert into the instantaneous velocity. Now, how can we get the direction of the instantaneous velocity? So, I am just taking the movement of a particle in the two dimension, and somehow it is moving on a curved path. Okay. So, how can we discuss the this one variation? So, the first graph indicate that the particle start its motion that from P and reaching to the P dash. So, here we have the displacement that is called the position vector from O to P is the R vector, and O to P dash is the R1 vector. Okay, we have. Now the displacement in this case will be by the help of the triangle of vector addition. You must analyze these graphs. Okay. So this one is the displacement delta R1 we have. Okay. Now corresponding time interval for this moment, that P to P dash. Okay. That is called the delta T1. Now we have to be limiting value of the time. limiting value of the average velocity. Okay, so we are just reducing the time interval. So in the second case I have taken the point p dash very much close to the, that means p. Here we have the displacement, that is called the delta r2 vector. Okay, so the position vector op dash is the r2, so that's why I have taken this one. And in this case the time interval, that means little bit shrink, so the delta t2 is time there. Now in the third graph we have the condition. Now the point p dash is very much close to the point p, so here we have the another kind of the displacement delta r3 vector, and the corresponding time is delta t3. Now here just I have assumed that the time interval is approaches to 0 between the two positions. Okay, and the p and p dash very much coincide to each other. Okay, so at this time the velocity is called the instantaneous velocity. Instantaneous velocity. So this is the simplest representations of the direction of the instantaneous velocity by the tangent to the path along the direction of the motion. Okay, so this is the representation. Here we have the relation about the times, that means delta t1 greater than delta t2 greater than delta t3. Okay, so this is the concern of the time we have. Okay, now here we can also show the displacement, that in delta r1 vector greater than compared to the delta r2 vector and greater than compared to the delta r3 vector in these cases. Okay, so whenever we are just assuming the condition of the instantaneous velocity, so we are just approaching the time interval that is equal to the 0, but not 0, not 0. Okay, so the concern part of the instantaneous velocity can be represented by that velocity, instantaneous velocity is equal to dy by dt of displacement. Okay, now the simplest exercise that is attached to the instantaneous velocity. Now the next opportunity we have, how we are just converting the instantaneous velocity in term of the rectangular component. So this is the simplest mathematical approach, and this one approach we will use in the part of the mathematics, because most of the equations those in the two dimensions are given in the part of the vector notation. So I have written that that means instantaneous velocity is equal to dy by dt of r vector. So I am just using the concern of the limit, that is delta t tends to 0, and this is called the delta r vector is to be divided by delta t. Okay, this is the simplest representations we have. Okay, so I am just approaching the limit delta t 0, and just delta r can be stated in the term of that delta x of I cap. These terms are coming from the previous sections. Okay, ij cap is the delta t. Now I am just separating all the things. So limit delta t tends to 0, delta x upon delta t, and this is the, that mean I cap, plus limit, either you can apply the separate limit delta t tends to 0, so this is called the delta y upon delta t, and thus jk. So what is the need of need to do this derivation? We want to know that how can we represent the, that mean velocities or the average velocities or the, that mean instantaneous velocity displacement in the part of the rectangular components, or along the two dimension or three dimension. Okay, so now we are just able to represent the meaning of the that mean instantaneous velocity in the part of the along the x-axis. So this one whole representation represented in the part of the x. Okay, so vx is the instantaneous velocity, okay, with the concern of the I cap, plus vy the concern of the j cap. So this one is the simplest representation we have. Now we can find out the magnitude from this term. Suppose this one is the equation number 1 we have. This one is the equation number 2. This one is the equation number 3. From equation number 3, what is the magnitude? So easily we are just applying the vector concern. So the magnitude of the instantaneous velocity, that is called the under root and a square of the components, that these are called the vx square plus vy square. So these are the, that mean components Okay, and how can we discuss the direction? So you have to be pay the attention that if the two vectors those are acting along the, that mean directions those are perpendicular to each other. So this one is the vx vector, this one is the vy vector we have. Okay, so this is the representation of the velocity, and this is the concern of the velocity, that is called the instantaneous velocity, which makes, and suppose the angle with the x-axis, that is called the theta. So easily we can go with the concern of the direction of the instantaneous velocity. So tan theta can be stated in the term of, that mean, perpendicular upon base. Yeah, just I am just putting the perpendicular here. So we can write that vy upon vx. Okay, so this implies that tan theta, sorry, this implies that theta inverse is equal to tan of vy upon vx. So this is the simplest, that mean, approach we have to convert the parameter in the term of the rectangular component. Okay, and somehow we can also represent the graph. Okay, suppose the object is showing the curved motion, and we are just getting a portion at which the 2 points very much close to each other in the graphical notation. So here we have the simplest notation. This is the portion, that mean O capital X and the Y, and along the x axis and y axis we are using. So this one is a Vx I cap, this one is a part of the theta we have, this one is a Vy and J cap. So this is the simplest representation of the concern, that mean of the instantaneous velocity in the part of the rectangular components. Now, dear students, we have the meaning of the average acceleration. That average acceleration is the ratio of the change in velocity and corresponding time interval. So the average acceleration is simply the ratio of the average velocity to corresponding time interval. Now I have the opportunity to resolve its component. Now delta Vx I cap upon delta T, delta Vy upon delta T j cap. Okay, so here we have the combinations along the x-axis and the y-axis. So I am representing the average change in velocity in the corresponding time interval by the ax vector and the, sorry, a, not, it is not a vector, it's a symbol of the average. Okay, here we have the symbol of the average. Okay, so this one is a representation we have. Now the instantaneous acceleration. So what actually the meaning of the instantaneous acceleration we have? Limit value of the average acceleration. Limit value of the average acceleration we have. Okay, when time interval approaches to 0 but not equal to 0. So instantaneous acceleration is the limit delta t tends to 0. Now dy by dt of velocity. Okay, so this is the meaning of the average instantaneous acceleration, and already we have discussed these portions in the part of the differentiation. Okay, now we can that mean go with the direction of the instantaneous acceleration and the average acceleration. Now the direction of the average acceleration. Direction of average acceleration is same as that of change in delta v direction. Okay, so this is the portion of the, that mean average that mean average direction of the portion of the average acceleration. Now we will talk about the direction of the instantaneous acceleration here. Now to discuss the instantaneous acceleration, I am just taking the help of the NCERT book in front of you, and this one that mean diagrams are available on the page number 75. So it's a very much easier to us to discuss these graphs. Okay, so what about in special in these graphs we have in the figure those are given that A, B, C, D. the thick line represent the blue line which we have, which represent the curved path of the object of the motion. Okay, object is at the point P, and at the time t, and at the p1, p2 and p3 and so on. We have particle will be at that mean particle showing the position after the time interval delta t1. Here we can include the delta t1, delta t2, delta t3. Okay, so in the fourth graph we will analyze this one in the last. Okay, so here we have, in the each case the change in the velocity is obtained. Here we are just taking the another representation of the velocities. Here just I am approaching the velocity by this help of the vector and v dash. So here we are just getting the meaning of the triangle. So delta v represent the average velocity. Okay, so in the next portion we are just reducing the time interval. So the point p2 is coming near to the point p. Okay, in the third case further we are reducing the time interval delta 3. So further point p3 comes to the point p, and in the last segment, whenever the delta t approaches to 0, so we are just getting the average velocity in the term of the that mean in the part of the that mean instantaneous acceleration. So here we have just average acceleration, the average acceleration in the part of the instantaneous acceleration, and here we are just getting the direction of the acceleration and the velocity, probably that mean having the some angle with each other. Okay, so we are just getting the different direction of the acceleration, that is called the instantaneous acceleration, and the velocity of an object. Okay, so it is an important concept which is given inside the NCERT, that in the one dimension the velocity and the acceleration of an object are always the same straight line in the one dimension. Okay, this one is the important portion we have. Now in the one dimension, what actually the velocity and the acceleration of an object are always along the same straight line, that either it can be opposite in the direction or either it can be in the same direction. Okay, however whenever we are just dealing with the motion of an object in the two dimension or three dimension, velocity and the acceleration vectors may have any angle between the 0 to 180 degree, and always there is a angle between the two vectors which act between from 0 to 180 degree. So here we are just getting the special that mean characteristics between the two vectors, that mean the angle between the instantaneous acceleration and the velocity of an particle which is given by it, that is having that different type of the angle. Okay, so this one is a basics we have, and through which we can go with the content of the numericals, that how we are just getting the numericals in the part of the rectangular components on this topic. So this is the purely the numerical based topic we have. Okay, now go through with these content that given inside your book. So somehow you can have the query, so you can contact to me. Okay, thank you, have a nice day.